Now when we talk about an octahedral complex, we know that all the bonds of an octahedral complex are equivalent. That is, they have the same bond length and they have the same characters. All of them are equivalent. You cannot say that this is a different bond length and this is a different bond length. No, every bond length is equal in an octahedral complexes. But for some complex this is not the case. For some complexes, 2 of the bond lengths can be very long and 4 of them can be shorter in comparison to them, or in other complexes 2 of the bond lengths can be shorter in comparison to the other 4 bond lengths. Why is this? This is because of an effect which is called Jahn-Teller distortion. So what is this effect, how this effect occurs, and in what complexes this effect occurs, we will see in our coming slides. Now, to first of all understand what is Jahn-Teller distortion, we need to understand what is energetic and electronic degeneracy. To understand, first of all, let us take the example of a p subshell. In the p subshell, you know there are 3 orbitals present, px, py and pz. That is px orbital, py orbital and pz orbital. Similarly, for your d subshell also, dxy, dyz, dz square, dx square minus y square and dxz. So in this case, in the p subshell, the energy of the px will be equal to py, which will be equal to pz, right? That is, the energy of px is equal to py is equal to pz. And in case of your d subshell, the energy of the dxy is equal to the energy of dyz, which is equal to the energy of dxz, which is equal to the energy of dz square, which is equal to the energy of dx square minus y square. This is what is meant by electronic degeneracy. That is, the energy of the orbitals, when the energy of the orbitals are same, they are said to be energetically degenerate. So now what is electronically degenerate? Here the px, py and pz can be said to be energetically degenerate. And the dxy, dyz, dxz, dz square, dx square minus y square, they are also energetically degenerate. Electronic degeneracy comes into play whenever there are electrons present in your orbital. Now let us say we have p subshell, okay, 3 orbitals. Now we have 1 electron. 1 electron we can put in any of the 3 orbitals. We can either put it in px or py or pz. It has equal probability of going into all of the 3 orbitals, because all of the 3 orbitals are same energy. So equal probability of going in any of the orbitals. That is, let us say it goes into px. Now I am going to put 1 more electron in to make a configuration of p2. So the second electron now has 2 options. It can either go into px, py or it can go into pz. But the main thing, it still has options. It has less options than before, but it still has options with it. So let us say I am putting it in pz. Now I am going to put 1 more electron in it to make the configuration p3. Now this third electron is not going to have any option because only 1 orbital is left, so it has to go into that orbital. P1 and P2 can be said to be electronically degenerate. Because the electron had options, so it is called electronically degenerate. Whereas the P3 is electronically non-degenerate because there were no options present. Electronically non-degenerate. Now after filling electrons, whenever an orbital becomes symmetric or the electrons are filled symmetrically, then that orbital is said to be non-degenerate, electronically non-degenerate. But when the orbitals are filled unsymmetrically, then the orbitals are going to be said as to be electronically degenerate. P1 is unsymmetrically filled, P2 is unsymmetrically filled, so that is going to be electronically degenerate. P3 is symmetrically filled. All of the electrons are half filled, it is symmetric. All of the orbitals are half filled, it is symmetric. So P3 is going to be electronically non-degenerate. So this is what is the difference between energetic and electronic degeneracy.